hour or so to just go over some problems. Okay, so the problem that we're covering right now is using a vector u, right? Just u1 dot 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 un to verify the following algebraic properties of Rn. Okay, so this one might be a situation where if this is the first kind of problem of this type that you've seen, it might look really abstract, but I promise you it's not too bad. So just first off, to sort of sync on the same page, are you familiar with what Rn is?
Not really. I
Okay.
thought it was just a matrix.
Rn is basically so if R1 is just the set of real numbers, R2 is basically all tuples consisting of a real number x and a real number y, right? So if R1 is a number line, 0, R2 is a grid, right? Just like an XY plane. And then
Okay,
R3 is so on and so forth, right? R3
gotcha.
is going to look like a 3D space, R4 is a 4D space, so on and so forth. Yeah, I can't really draw it after 3, right? Um, X, Y, Z. So what this is asking you is, let's try to be, I think, a little abstract here and say that for any n-dimensional space, Rn, we have some vector u, which goes from u1 dot 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 un. Any issues with thinking about in like arbitrary vector u, or are you reasonably comfortable with this concept?
I
Um,
think I'm good with that.
yeah, it's basically just saying that show that for any vector u that exists inside this space, right? So it's not for any vector u, it could be zero, it could be the zero vector, it could be um, some unit vector, it could be some massive vector pointing in any direction, right? It's saying that show that these properties are true. And a lot of these are hopefully pretty intuitive if you can think about them from the sort of one-dimensional example, right? This is basically, so think about one dimension where u is just a straight up number like 5 or 7.5 or pi, right? For any of those numbers, adding it to its own negative is equivalent to adding its negative to the positive version, and then all of those are equal to 0, right? So in one dimension, or hopefully even two dimensions, this is pretty, I hope this is pretty obvious. It's basically saying any vector u, add it to its opposite, and you'll get 0.
Oh, that's
Yeah,
not too bad.
right. So it's pretty intuitive when you say it like that, right? But how do
Yeah.
you make it a tiny bit more rigorous and prove it in terms of uh, vector addition or vector subtraction, right? So let me just draw out. Oh, I realize my screen is kind of blocking my whiteboard. Oh gosh, when I was drawing this entire time, was my screen being blocked
No, no,
off?
no, no, no.
Okay,
You can see
all
all
right,
of it.
that's great. So negative u is basically minus u1. Sorry, it's basically this thing, right? I'm forgetting to write my commas. Any issues with this? Negative u is basically just taking each of these individual u1, u2, u3, and taking the
And just
negative
making them
version,
negative.
right? So then, do you feel like you're pretty confident at this point you could show that adding u and negative u is going to give you 0? You can just look at the element-wise addition and whatnot.
Yeah, they're all just going to cancel each other out.
Yeah, exactly. And it doesn't matter which one you add first. You could be u and negative u, or the other way around. It's all going to be 0, just like the thing claims, right? So hopefully that's okay.
Yep.
Okay. So then, do you feel like that sort of takes care of the next one as well, where it's asking you about what is this? So now there's no negative u; it's just c times du, and you want to show that that's equal to cd times u, right?
Yeah. Once you go down to like the one-dimensional thing, like you were talking about, then you
Yeah.
could just
Well,
use that
yeah.
justification.
Hopefully,
Right?
you think about it at like this level of granularity, where you're using the u1 dot 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 un, right? And then you can just um these vectors behave exactly as you would hope, where du is equal to uh, d. Like I'm the way to write these proofs is to literally just start with what's over here and then just try to massage it into what's over here, right? So I would write c du as c times d times u1 dot 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 un, and then I would move the d inside so that it's du1 du2 dot 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 etc. And hopefully you can just sort of massage around it from there.
Gotcha.
Yeah. Or, well, this is actually really silly because I'm, yeah. Anyways, okay, so I think the wording here is a little bit silly and results in maybe some ambiguity, but like, I think it's understood that maybe du to begin with is just du1 dot 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 dun. Maybe that's the way to make this problem. Sorry, I'm overcomplicating it. Yeah, I would say that du is probably just interpreted as something like this. You can interpret it d, inside or outside the parentheses. It doesn't matter. But the point is to show that you can massage this to turn it into this, where the CD is out in front, and then the U is sort of by itself,
Yeah.
or sort of isolated it out. Anyways, I hope that makes some sense. Okay, so then on for the last one. Or what is the last one? Was it 30, 44? 42?
I think it was 42 again,
40,
just 1.4. 41, sorry.
41. Gotcha. Okay. Yeah, here it is. Okay, so this, have you learned about like rank nullity theorem or rank kernel theorem or anything like that yet?
I mean, we talked about it, but
Okay.
uh,
Well,
I
this
didn't
one's
understand.
pretty good and conceptual, and I can sort of talk through intuition and leave the proof for you. But let's just sort
Okay.
of draw out. Um, okay, so let's just sort of draw out this. So A is a 3x2 matrix. So I think it's always kind of good to make sure your head is screwed on straight in terms of how to interpret the dimensions. So 3x2 means 3 columns and no, sorry, 3 rows and 2 columns. But okay, back to it. So this is ax is equal to b, right? And here x, you can always, by the way, here's a little trick. X is going to be 2 by 1, right? So this is 2 and this is 1. And you can remind yourself that 2 and the 2 here need to match because of just how matrix multiplication is defined. And then when you're multiplying two vectors together, right? If you have a 3x2 matrix multiplied by a 2x1 matrix, a shortcut to remember the what do you call it, the results, is basically just look at the first and the last thing. Yeah, it's sort of like sandwiching them together, and then like the 2 goes away, and you're just left with the outsides. It's a
Okay.
little mnemonic that is surprisingly helpful if you're as forgetful as me. So B is 3x1. So let's put this in intuitive terms, right? It's asking us to show that it cannot be consistent for all B in R3. And so B is essentially, X is essentially the input, B is essentially the output. So this is saying in English, a linear transformation A that maps from two-dimensional space, because X is a two vector. Or, sorry, that's the wrong phrasing. X lives in a two-dimensional space, B lives in a three-dimensional space. So it's impossible to have a linear transformation that sends R2 to map to all of R3. Is that believable? It's sort of saying
Which is
like,
what?
what's up?
Which is why it has one column.
Um, so hold on, what do you mean?
Because oh wait, no, because there's only 2 rows.
So like if R2 is like a XY plane, for example, and R3 is a X, Y, Z, a 3D space, this is basically saying that there's not enough stuff in in R2 to map onto everything in R3. That's sort of intuitively what it means. And that's not a proof by any means, but like, does this feel kind of believable? It's like, at least under a linear transformation, it's you just don't have enough stuff in R2 to be able to map onto everything in R3.
Right. Yeah,
Yeah.
that makes sense.
Yeah. Like, don't be too confident about that because, the fact that it's linear is very important. You could probably come up with contrived transformations to, you know what? Actually, I don't remember. but just intuitively, right? This is an issue because like there's just not enough dimensionality in here to be able to map onto everything in the three-dimensional space, right? It's hard to map a square onto a cube. Okay, so this is the intuition, and hopefully that's somewhat believable. But okay, in terms of proof, do you know what rank is, right?
Let's just go over it just to make sure.
Sure. So rank, yeah, I'm struggling to use the precise wording because it's so long since I've taken this myself. But rank is basically when you do reduced row echelon form, right? Rank, one way to think about rank in the most like dry way is how many leading ones there are after you've done reduced row echelon form. And the fact that there's a 2 by 3 matrix, sorry, the fact that this is a 3 by 2 matrix means that, well, there's only so much room, right?
Okay, so rank is like pivot points, maybe is what they're calling it in this class.
Oh, they're calling it pivot points?
Yeah,
I've never heard of that phrase, but
yeah,
if that's the
I'm
same
sure it's the same
concept,
thing. It sounds like the same thing.
okay, gotcha. But the idea here is that because this matrix, you know, the smaller of the column number of columns or the number of rows is gonna be like an upper bound on rank, right? Like it's just impossible to have more than two leading ones when you only have two columns, right? Because you literally have two columns. How can you have and the last one is gonna get sorry zeroed out once you do reduced row echelon form. But
Right.
basically, do you believe me that there's at most two pivot points or at most, you know, rank two, right? Look, the columns of A span Rm. There we go. You see this? The columns
Yeah.
of A span Rm. And for each B in Rm, the equation Ax is equal to B has a solution. So M here, M by N in our case is 3 by 2. So this is saying A is a 3 by 2 matrix. And for each B and R3, so basically for each B in the output space R3, the equation Ax is equal to B has a solution. And that's true if and only if the columns of A span R3. But there are only two columns. So how can you possibly have two vectors spanning a three-dimensional space, right? You can't. And
Gotcha.
that's sort of the, you know, maybe how to word this uh in terms of what this textbook's language is. So I think, you know, I don't think I've given you everything. I think there's still plenty for you to play around with and, you know, maybe cement or try to figure out try to figure out all the details, right? But hopefully you're in a
Yeah.
reasonably comfortable spot with this now.
Yeah.
Okay.
I can solve it.
All right, yeah. So I mean, this they've given this to you, right? They've given you this theorem, and this theorem, I think, could be a really powerful tool for you to solve this problem with, right? The fact that all of the statements are true or all of them are false, right? Well, we know that C is false, so we know that, yeah. So maybe you have to do a little bit of work showing that C is in fact false, but hopefully that should be pretty intuitive.
Got it.
See if you can find in your textbook anywhere else discussing a connection between span and the number of pivot points, right? Like let me put it this way: if you were talking to like sophomores or juniors who've had, you know, reasonably comfortable with linear algebra, the moment you told them this, they can immediately make the conclusion to this, right? But because this is a introductory class, maybe it's expected that you do a little bit of work in proving that statement C is false in this particular problem.
And then I had one more question, maybe no trivial solutions. Do you know, or non-trivial solution? Do you know how to explain what that is? Because we were
Yeah,
going over it and I
trivial
just
has a very specific meaning in linear algebra. So trivial solution uh, solution is when x is equal to 0, when every single x is equal to 0. Right? A vector is called trivial if all of its coordinates are 0, if it's a 0 vector, right? And in linear algebra, we're typically interested in finding non-trivial non-trivial solutions. So like big picture wise, um remember in regular algebra where we're interested in trying to find we're trying to find the zeros, right? Things that map to zero. So like in regular algebra, right, you might be trying to find the roots of a parabola. We're trying to find the points x that map to values of y that are zero, right? Linear algebra is actually quite similar. It's just in higher dimension, um, and things kind of have to go through the origin, right? Whereas in regular algebra, we're allowed to have y is equal to mx plus b. In linear algebra, you can't have the plus b. So with that said, linear algebra, a lot of the times we're interested in okay, so obviously if x is 0, y is also equal to 0, right?
Yeah.
But in linear algebra, you could have other cases where um, because it's in a high dimensional space, you could have situations where uh, ax maps to some value of 0 for non-trivial x, right? For x that's not all 0. And usually that means something very interesting is happening. That's sort of super high level, oversimplified explanation. But yeah, that's
Works.
yeah, trivial pops up so many times because when you talk about there being a linear combination, right? A linear combination such that ax1 plus bx2 plus cx3 is equal to 0. When all of them are equal to 0, that's not very interesting at all, right? Because the fact that it's linear algebra, the fact that we don't allow a plus b, so to speak, in linear algebra means that we're already guaranteed that the solution of all zeros is a solution. And we're interested in things that sort of go beyond this baseline. Yeah. But anyways, I think I'll wrap up the thing there. By the way, it sounds like you had a friend joining us. I just wanted to make aware that we were making a recording of a couple of problems we were discussing. But we'll end it now.